And we continue with the last talk of this session and of this conference by Fabian Beutel. The title is Ultrafast Waveguide-Integrated Single-Photon Detectors for On-Chip QKD Detection. So we move on to something completely different.
Okay, thank you for the introduction. So my name is Fabian Beutel, and I'm from Münster University in Germany, from the group of Wolfram Pernice. We do single-photon detectors, and to be more specific, we do nanowire single-photon detectors. Today I'm going to present you our devices, which are, first of all, very fast. So this is a nice property, of course, also for QKD. And secondly, you can integrate them with other photonic elements, which is also nice for QKD experiments. So first of all, in the first talk of this week, I think by Christoph Marquardt, you already saw this table comparing different detector technologies. And essentially, when you look at detectors, there are different metrics that we are interested in. And of course, most importantly, also for QKD is the efficiency, dead time, and of course the dark count rate, but also some other properties. And you'll see that in most of these fields, superconducting nanowire superconducting nanowire SPDs are actually state of the art and is what we actually would like to use because they have so good properties. So superconducting nanowire SPDs is also what we are working on. And to explain a little bit what we did and what our results are, let's first have a little closer look at what a nanowire actually is. So in principle, the detector is in a setup like this. So you have basically two contact pads in between this nanowire, which consists of a superconducting material. So in our case, we use niobium nitride, but there are also other materials. And the superconductor is, of course, only superconducting if the current that flows through it is below a so-called critical current. And now what you do is you send a bias current through this wire, which is just right below this boundary, so to speak. And then if a photon actually gets absorbed by this wire, we have some local effect. So that's actually a hotspot is created in this nanowire, where locally the superconductivity will break down, which then leads to higher current in the outer areas or in the other areas of the nanowire, so that eventually in the whole nanowire, the superconductivity will break down. And now if you look here in the right, basically you can represent this nanowire as this red part. So due to its geometry, it forms a kinetic inductance. And also this kind of switch, it can either be in this superconducting state, then we have no resistivity, or it can be in this resistive state. And in this case, if we have a parallel resistor next to the nanowire, we will only see a pulse here, a current pulse or a voltage pulse, if actually the superconductivity breaks down. So this is the basic working principle. And if you look at commercial detectors that work, most of them work in this way, you will actually notice that the counting rate is somewhat limited. So there always seems to be this bound of somewhere about around 100 megahertz. And also outside I found a booth. So I don't speak Chinese, but I think I can recognize a pattern here. So somehow there seems to be this limit of count rate of 100 megahertz. And to understand where this comes from, we have to have a little closer look at this voltage pulse that we can measure. And so basically, it consists of this rise time and the decay time of this pulse. And it turns out that this time, how long this decay time will be, is directly proportional, to this kinetic inductance that the wire geometry defines. And this again is dependent on the wire geometry. So it's proportional to the length of the nanowire and inversely proportional to its cross section. Now, the cross-section, if we want to increase that, we have a problem, because if you make the wire just wider or larger or thicker, then one photon will not be enough to actually trigger this breakdown of superconductivity anymore. So we cannot do much about the cross-section. On the other hand, the length, and now this is one of the weaknesses of this design, we also cannot change arbitrarily, because since the light is here incident from the top, so perpendicular to the wire geometry, we actually need to make the wire large in order to cover the whole area of the incoming light beam. So if you make it smaller, then we don't catch all the photons anymore, and hence this efficiency suffers. Also, a second downside from this approach is that you cannot really integrate it with photonic elements on a chip, because, as I just said, the light is coming from the top onto this wire, And so if you have your light in a waveguide coming from other photonic elements on your chip, there's no easy way to actually transfer the light from the waveguide into this nanowire. So in our group, what we use instead are so-called waveguide-integrated nanowire detectors. And essentially, here in blue, you can see a waveguide. And most of the time, we're using silicon or silicon nitride, but you can also use other materials. And essentially, you couple the light into this waveguide, and then you just place this short U-shaped nanowire on top of it. And this also has the same working principle as the other nanowire, and we can also, with this design, achieve 85% on-chip detection efficiency, very low jitter that is comparable to the other devices, and also very low dark count rates. Also, because we basically only have this one turn of the wire, we also have a reduced dead time that is a lot better than in these very long wires that you have in this other design. To see why they are so efficient, we can have a look. So this is an SEM picture on the top, and on the bottom you see a simulation of the light that is actually traveling through the waveguide, and you'll see that after some microns of this wire, all of the light is already absorbed by the nanowire. So there's really an absorption that is close to unity here. And then since the wire is also very efficient, since we made it so thin, as I explained before, we get a very high detection efficiency. Now the question is, can we make this detector even faster, and can we make it, and how can we do it? Of course, the first idea is to just make it shorter. And the shortest you can make this wire, essentially, is to just get rid of this U shape and make a single waveguide crossing wire. So this is also what we call the bow tie geometry, where essentially you just have this single crossing across the waveguide. And in fact, it turns out that really with this design, you get an extremely fast reset time, so extremely low dead time of your detector. So here we are talking about less than 500 picoseconds of reset time. But of course, there's a price to pay, and it's the efficiency. Because if you make it that short, then in the end, the interaction length of the wire is very short, and you won't have much absorption anymore. To compensate this, we just place this short nanowire in a photonic crystal cavity. So basically, we add a front reflector and a back reflector. And by using this so-called cavity-enhanced SNSPDs, we reach quite a good performance of 30% on-chip detection efficiency, or almost 30%, while keeping this very small recovery time. And as a nice side benefit, we also get even lower dark count rates, because this cavity then acts as a resonance filter, and only the light that we actually want to look at triggers a click. Now, the question now, this was from 2 years ago, this paper, and the question is now, why can we not reach higher efficiencies with this design? The reason is mostly that in order to carry this nanowire, below you still have some kind of support structure. And in our case, it's the same material as the waveguide, so it's silicon in this case. And each time the light passes this waveguide crossing, you'll have some scattering losses. And so even if you simulate it just theoretically, you'll see that you're somehow limited in the absorption that you can reach at a maximum. So now let me present you the newest generation of devices where we kind of try to overcome this problem. And we do this by, instead of using a one-dimensional cavity, we now employ a two-dimensional photonic crystal cavity. And it looks somewhat like this. And you cannot really see the variation in the holes by the naked eye. But so it varies along this length of the cavity. And all these holes, this photonic crystal, then basically, first of all, it defines as a waveguide in this area. And secondly, it gives us here a front reflector region, a back reflector region, and then in the middle, our cavity region. The big advantage of this design is now that we don't need an additional support structure for this nanowire, because we can just place the nanowire on top of the cavity. And now the cavity itself basically is the support structure, so we don't have any crossings in the waveguide anymore. And in fact, with this detector technology, we really can reach efficiencies that are close to 70%. So around 1504, but this is due to fabrication inaccuracies. But so we reach almost 70% detection efficiencies, and the dark count rate is exceptionally low. So we measured for a few hours, I think it was 2 or 3 hours, and we didn't measure a single dark count with this detector design. So this is just also an upper bound. Also, the jitter behavior is actually very good. As you can see, it's even below 30 picoseconds, which is also almost state of the art. So the most interesting thing, because I talk, of course, about ultra-fast detectors, is to look at the timing characteristics. And here what we've done is we send a CW light onto these new kind of detectors. And then after one, so essentially since you have very low CW light, you expect the pulses to be distributed equally, uniformly, if you look at the time axis. And so what we do is we look at click, which occurs at a 0 time, and then we add up when all the subsequent pulses basically on the time axis happen. You see that after 500 picoseconds already, we reach this uniform distribution again. So our detector is fully recovered and fully responsive again. So this allows us for detection rates at full efficiency of up to 2 gigahertz already. You also see, moreover, that after half this time, so after 250 picoseconds, clicks already start to being registered again. So of course here you have a lower efficiency, but this just shows you how fast essentially our detectors are, because even after this short amount of time, you are able to register clicks already. So these are our very fast detectors, and to show you the second big benefit, namely the integration with photonic circuits, I just want to give you 2 example applications why this is very nice. So first of all, last year we built this on-chip single-photon spectrometer, which we combined with our SNSPDs. So the spectrometer works as follows. You have here one input waveguide, and then you separate this light. This comes into many outgoing waveguides, and then at the end you lead them all together again. And depending on the wavelength of your light, you'll have constructive or destructive interference at one of these output ports. And now what we can do, because our detectors are nice and small and also easy, so this doesn't add any additional fabrication steps. It's very easy for us to just place one detector at each output of this spectrometer. And so basically each of these things here is a nanowire detector that we have. So we have 8 of them in total. And with this, we realized a nice single-photon spectrometer just on a single chip. So this is a very small device, obviously. And in this case, we had a channel bandwidth of 2 nanometers, very low crosstalk of -18 dB, on-chip detection efficiency of about 20%, but this is mostly due to the losses that occur in this arrayed waveguide grating that I showed you before. So there we just have, so on the upper graph, you see the transmission without any photon detectors. Just if you build the device by itself, you already have quite some losses. And then, of course, you end up with a lower detection efficiency in the end. However, in principle, you still have a nice efficiency that allows you to analyze single photons. So this is also an application that could be interesting for QKD if you work in the frequency space, to actually do the frequency measurements directly on chip. This was also demonstrated for 2 different wavelength regimes. So first at the telecom wavelength, and secondly also with visible light. And this shows how flexible also this this waveguide-integrated nanowire design is, because basically they are pretty much wavelength independent. Of course, you have to adapt the design a little bit, but in principle, you can use them at any wavelength range. The second very nice experiment that we performed was to build a chip that included a single photon source and single photon detectors on one single chip. In this case, the single photon source that we used was a carbon nanotube. It was performed by the group of Ralf Krupke from TU Darmstadt. And what we wanted to do actually in this experiment is to characterize the single photon source with our detectors. And so what we did is just to place one detector on each side of such a waveguide. So you basically, the light from the emitter couples into this waveguide, and then you have one detector at each side. And naturally, what you do with a single photon source is you perform a G2 measurement, and this is what we did. And we're barely below this magic limit of 0.5 here, but we are below. So essentially, this just demonstrates a very nice application where you can even combine single photon sources and single photon detectors on one single chip with our platform. So to sum up, first of all, I showed you our newest detector design, which allows for extremely fast detection rates. So here we're talking about somewhere around 2 gigahertz detection rates that we allow with this device, while keeping very good detection efficiencies of 67% and also having exceptionally low dark counts. Secondly, a nice benefit is you can integrate these detectors with other photonic elements like resonance filters or for instance, single-photon sources. So this is really a very good platform, basically for establishing, when you go to on-chip QKD also and on-chip photonic integration. Let me end with a small advertisement here also. So we're based in Münster, Germany. So from Münster University, we're actually located here at the Center for Nanotechnology. And of course, we're also always interested in cool ideas or projects where we could employ these detectors for QKD or say related technologies. So if you're interested, just send me an email. And our website is hiding behind this QR code. We also have very nice nanofabrication facilities at our place. If you're interested, just come and talk to me. So with this, I want to thank you for your attention. And if there are any questions, yeah.
Thank you. Are there questions for Fabian? I see one up there.
Oh, very nice work. I have two questions. The first one, how fast has your chip reached? That is the real maximum count rate in the lab up to now. You estimate it is 2 gigahertz from the recovery time, 500 picosecond. And how about the real count rate, the maximum one?
I think I didn't really get the second part of the question. So you're talking about this reset time, right?
Yeah. The 2 gigahertz comes from the recovery time of 500 picosecond.
Yeah.
How about the real count rate you got in the lab?
The real count rate in the lab. Okay, this is a somewhat difficult question because usually if you have counting electronics, like state-of-the-art counting electronics that you can use, they usually have a much larger dead time than our detectors. So usually they have something like 90 to 100 nanoseconds. So it's difficult for us to directly measure this, this count rate. However, so we did this, indirect measurement, and here, so we zoomed out even beyond the 100 nanoseconds of dead time, and you always see this this uniform distribution, which lets us conclude that the maximum count rate is actually this 2 gigahertz. And to back this up a little bit, maybe I have this backup slide. So what we can also do is, so if you look at the right part of this slide, what we did there basically is we sent some two consecutive pulses and delayed them by first 250 picoseconds and then 500 picoseconds and then also longer delays. And we saw that from 500 picoseconds we already, so the second pulse is already detected with this full efficiency again anymore. So we always only measured in this setup 2 pulses that come one after another, just because the counting electronics, we didn't have to measure full count rate. And we did all this performance with all these measurements with an oscilloscope and then just analyzed the traces instead of using counting electronics. What? Yeah. Exactly. So we record a long trace, so about 100 nanoseconds, and then count all the pulses and do this a few million times, and then we can conclude about the maximum count rate. But this is only because we don't have the electronics, because they are very expensive, and yeah.
And the second one, in your second work, how to determine the placement of the single nanowire, since I find the direction of the nanowire is not vertical to the direction of the cavity. Not this one. The photonic crystal cavity.
You mean this one?
This one. Yeah, the direction is not vertical to
this is basically you can look at the mode profile that you can see here on the right, and so we played with different configurations there. But in this case, this turned out to be one of the more efficient ones. And you can also see that here in this mode profile inside your cavity, this is where you will get most of the light inside your cavity.
I see. Thank you.
Welcome.
I see a bunch of more questions. First one here.
Me?
Second,
Okay.
third.
Just a quick question. I guess these waveguides are single mode gratings?
We are working with single mode waveguides.
Yeah. So what's your coupling efficiency to the waveguide?
not very good in our case because just for testing purposes we use grating couplers. So there we really have high losses of 7 to 8 dB usually. So this is why we also always measure the on-chip detection efficiency, not the system efficiency. We somewhat consider this problem of coupling into the chip not as our part of the work, because I mean, in the end, it's kind of engineering work that has been done already. And for us, it's very convenient to use these grating couplers because then we can place really many devices on a chip, have the stage inside the cryostat, and then just move and couple in vertically. So this is very convenient. But of course, if you would use this in a, say, I don't know, commercial product, you would of course use other coupling technologies like butt coupling or, yeah.
Thank you.
So I have 2 more questions.
Actually, this is not an issue for this in future because the photodetector and the light source integration on chip, so no interface coupling problem. So the 3 dB is the takeout. I help you to answer the question for that.
Yeah. Okay.
But if go to the long distance and total integration on chip, so this is wonderful for quantum people. All right, I come to my question. The first page you show all of the photodetector of this one, and after you finish this project, compare with other single photon detector. What's your advantage? What's your advantage? What's your
the advantage of our?
And it also need a cooling system?
Yes, so we also need a cooling system, so we are working at 1.6 Kelvin, so it's not like too low, but I mean, if you increase the temperature, you will see an increase in the dark count rate due to blackbody radiation, but it's not like we need to go to millikelvins or something like this. So this is still doable with a standard off-the-shelf dry cycle, closed cycle helium cryostat.
What's your opinion on compare with semiconductor-based photodetector, single photon detector?
Semiconductor-based? Well, I guess
the 2 technology, the potential.
Yeah, to compare the technology, yeah, I mean, I guess since you have a much lower dark count rate, I think this probably is the biggest advantage in the context of QKD, and also not having to operate it in gated mode due to having this lower dark counts, I think is a very big advantage of our in general of this SNSPD technology, because it allows you to, yeah, if you don't have to gate and you don't have the dark counts anymore, which essentially, yeah, I think this is probably, besides the speed that you obviously have, the largest advantage, I would say. And also that you can nicely integrate it with these elements. I mean, I don't know about any waveguide-integrated APDs, so yeah.
All right, let's thank Fabian again.
Thank you.